Hello friends, you are welcome to our YouTube channel JK Academy India. In this video, we will discuss about the three-phase transformers. Before to start three-phase transformer, it is necessary to learn the characteristic of balanced three-phase system as well as conventions followed to designate currents and voltages of a three-phase system. If the supply voltage is balanced, the voltage can be represented by a voltage triangle shown in this figure. So this is the voltage triangle. ABC are the nomenclature for three lines of the system, and N stands for the neutral of a star point of system. ABC are the three vertices of equilateral triangle, and N is the circumcenter of this triangle. The voltages and currents with double scripts notation are represented by phasor. This is VAB, voltage across A and B, VBC, voltage across B and C, and VCA, voltage across VCA. Whereas this is voltage across VA with respect to neutral. This is the voltage across V and B with respect to B phase and neutral, and this is V and C, voltage in between phase C and neutral. For example, VAB and IAB represent voltage of point A with respect to point B and current flowing from A to B respectively, with the arrow pointing towards A. The line represents the voltage phasor AN. Thus line to line voltage, also called line voltage phasor, and line to neutral voltage, also known as phase voltage phasor, and can be drawn from the voltage triangle by this. And the phasor diagram shows where phase voltage phasors, which are equal in magnitude, are displaced from each other by 120 degree. The line voltage phasor are also equal in magnitude, displaced from each other by 120 degree. In any three-phase system, there are R, Y, B, or you can say A, B, C, three phases, and the voltage vectors are always displaced by 120 degree apart from each other. And in balanced system, the voltage across VAB, VBC and VCA should be equal. If the system is star connected, then the voltage across VAN, VBN and VCN should be equal. Further, it may be noted that the set of line voltage phasors is displaced from the set of phase voltage phasor by 30 degree. Suppose this is a VAN vector and this is VNB vector of phase voltage, then the line voltage vector VAB is 30 degree phase displaced with respect to VNA. Okay. If the lines carry balanced load, then the magnitude of line current A, B and C are equal and displaced with respect to each other by 120 degree. They are equally displaced from the corresponding phase voltage by an angle phi as shown in here. This is the phi. The power factor being the cos phi, in this case the power factor is lagging as the current lag behind the phase voltage. Important relations in three-phase connected system. In star connection, this is your star connection, this is neutral, and this is your delta connection. So in star connection, line voltage equals to root 3 phase voltage. But in delta connection, line voltage equals to phase voltage because there is no neutral. Whereas the line current equals to phase current in star system, but in delta system, line current is root 3 of phase current. But the power equation in both star and delta will be root 3 VL IL cos phi, or it can be written as 3 times of phase voltage and phase current into power factor. In three-phase transformer, primary side, the induced EMF per phase equals to 4.44 F phi m N1, and in secondary, phase induced EMF is 4.44 F phi m N2. You can write phi m as Bm into Ai also, where B is the flux density, A is the cross-sectional area, and phi is the flux. And the transformation ratio K equals to voltage in phase 2 divided by voltage in phase 1, means secondary voltage divided by primary voltage, or number of turns in secondary winding divided by number of turns in primary winding, N2 by N1. Now, in three-phase system, the connections can be made in four ways, and they are grouped as 1, 2, 3, and 4. If there is a 0-degree phase displacement, then connection symbolic notation can be denoted as YY0, DD0, and DZ0. If the phase displacement is 180 degree, then symbolic notation will be YY6, DD6, and DZ6. In group 3, if the phase displacement is 30 degree lagging, means secondary induced EMF is lagged by the primary induced EMF at an angle of 30 degree, then it will be denoted as dy1, yd1, yz1. If 30-degree lead phase displacement is shown, that falls in group 4, then the symbolic notation will become dy11, yd11, and yz11. Here Y is for the star connection, D is for the delta connection, and Z is for the zigzag connection. This is Y, this is D, and this is Z. First letter indicates the primary winding connection, and second letter denotes the secondary winding connection. Now let us see group 1 having 0 degree phase displacement. First connection here shown as YY0, where the HV winding is connected in star and LV is also connected in star. This is the phasor diagram of the induced voltage in HV winding, and this is the LV winding. So all the vectors of HV and LV having the same phase displacement and there is no change. Now DD0 connection. Here the primary winding is connected in delta, secondary winding is also in delta. So the phasor diagram will be like this. This is for HV and this is for LV. This is DZ0. HV winding is connected in delta, whereas the LV winding is connected in zigzag connection. So this is called the zigzag connection. Each winding having two sets of winding, means one phase winding is divided in two sets. One set is sorted and neutral is taken out from this. This type of connection is called the zigzag connection. In this case, HE winding vector delta will look like this, and the phasor diagram for Z zigzag winding will be like this. Now group 2 having 180 degree phase displacement denoted as YY6, where the star winding is connected in star HE winding, LV winding is also connected in star, and the phasor diagram will look like this. Here A1 is upward, A2 is just downward, so there is a phase angle difference of 180 degree, means secondary voltage is displaced 180 degree with respect to primary winding. In DD6 connection, HE winding is connected in delta and LV winding is also connected in delta, but there is a phase displacement of 180 degree. Here again A1 and A2. Now DZ6, primary winding or HE winding is connected in delta, where the LV winding is connected in zigzag, and the phasor diagram of 180 degree phase displacement will be look like this. This is A2 and this is A1. This DZ type transformers are mainly used for the transformer having delta winding, and we need to uh, provide the earth fall protection. So one delta transformer is connected to HE winding, and this neutral is normally grounded by connecting a resistor that is called neutral grounding resistor, NGR. It can be seen mostly in power stations, in case of generator also, and in a very high voltage transformers, because if there is a delta circuit and we need to find the earth fault, then there is no path. So by connecting a DZ transformer or zigzag transformer, we are providing fault current to flow through the neutral and limiting by a resistor. Now, group 3 having the 30-degree phase displacement, and here the phase displacement is in leading. First one is the dy1. HE winding is connected in delta, LV in star. HE winding having this phasor diagram, LV will be like this. So A1 is leading with respect to A1 of HV by 30 degree. YD1, HE winding in star, LV winding in delta, and phasor diagram will be like this. YZ1, HE winding in star, LV winding in zigzag. Phasor diagram will be like this. This will be A1 and this will be A4. Group number 4, 30-degree phase displacement. dy11, HE winding is connected in delta, LV in star. Phasor diagram will look like this. Here A1 is HE winding A1 is lagging and LV winding A1 is in leading. Now YD11, HE winding is in star, LV winding in delta. This is the phasor diagram of LV and HV. This is the YZ11, HE winding in star, LV winding in zigzag, and this is the phasor diagram. So in this video we have discussed the different type of connections made in three-phase transformers. So thanks for watching. See you in next video. Take care and goodbye.